Okay, continuing on with electrical energy and power. Batteries convert chemical energy to electrical energy, which is then converted to some other form of mechanical energy. Perhaps, like if you're turning a motor or whatever, or thermal energy, or perhaps light, as in like a light bulb. Thermal energy, like in a heater or a light bulb, which produces really mostly heat. Now, it's useful then to be able to describe the amount of electrical energy, and we'll use this quite a lot in your homes, provided by a circuit. If you remember, our change in potential energy was equal to Q times delta V. And so since power is energy over time, if you recall from last semester, power is just a measure of the amount of energy per time, then I can describe this as Q delta V over delta T. But notice here that Q over T, that's just current, right? That's Q over T is our definition for current. So I can replace that with current, and I get an expression for power, which is going to be my potential times my current. So power is equal to the voltage times the current. This applies to any electric device, and you'll notice in your homes that the current is, or excuse me, the power ratings are listed on the device, and we'll talk about that in a bit. Now, the unit of power, just like last semester, is the watt. The what? The watt. It's the watt. It's abbreviated with a capital W, and 1 watt is equivalent to 1 joule per second in the SI system. Now, we can use Ohm's law just to make some substitutions, and you have these equations on your equation sheet. Remember, V is equal to IR. So I can just plug that in on here, and I can get P is equal to VI. That goes back to our original derivation for power. But if I plug in IR for V times I get an alternate expression for the power, which is I squared R. And then you can do another one where you say VI was V times V over R, which is going to be V squared over R. So both of these are equal to power, or the same power. And you can also have the original expression that we derived. So let's do some sample questions. Okay, these are just some MCAT questions. We'll take a knockout at these. These are a little bit different topic. But if I have a current of 1 amp that flows through a circuit for 5 seconds, how much charge is flowed? Well, this goes back to our definition for current. I is Q over T. I want to know Q. Q is current times time, 1 amp times 5 seconds. So that's going to be 5 coulombs. An amp is a coulomb per second. R for two identically shaped conductors is in a ratio of 1 to 2. And what ratio must their resistivities be? Well, first of all, let's just write this expression. And that is to say that R1 is equal to 2 times R2. I have this 1 to 2 relationship. And since I know that R is proportional to rho, then I would say that rho 1 has to equal twice that of rho 2. Okay, so the answer here is 1 to 2. All right, and then the next question is related to power. So the transformer transforms an input voltage and produces an output voltage that is larger or smaller than the input voltage. We'll see this a little bit later when we get into at-home electrical systems. We'll talk about transformers. But a transformer, basically, it's this metal can, and you have these high voltage leads that come in, and then you get some leads that come out. These are high voltage. These go to your house, and they're low voltage. These can be on the order of about 3,000 volts or so. But that comes into your house is only 120 volts. All right. So how do I get down from this very high energy per unit charge to very low energy per unit charge? That doesn't really seem to make any sense, because I'm seemingly losing energy as I take this high potential, which is energy per unit charge, and bringing it down to a lower potential so that we can use it in our house at a safe level. All right, so this question deals with that. It says a transformer produces V out that's 300% larger than Vn. So in this case, Vn is going to be a low voltage, and then it outputs a high voltage. And I want to know what is the ratio of I out to In. Well, I know that the power, the output power, has to equal the input power. This is just from the conservation of energy. And unless I have another source of energy somewhere, I can't just create energy. All right. So I know that my output and my input powers have to be the same. And so V out, I out has to equal Vn, In. All right. But I know, just from what it says, that V out is equal to 3 times Vn. I'm getting a much higher output voltage than my input voltage. So then, because of this, I can find a relationship between I out and In. So let's see, I'll just put this here. V out, I out equals 3. Actually, let me rewrite this just a little bit. I'm going to replace this with 3 times Vn, right, which is V out. And then over here, I'll have Vn, In. Okay, my Vn's cancel, and I'm left with an expression, our ratio of I out to In. Equals 1 to 3. All right, so my I out, the outgoing current, the output current, is 1/3 that of the input current. So that's where the answer comes. How I get from this high voltage over here to this low voltage is that over here I have a high voltage, but I have a very low current. And over here I have a low voltage, but I have a very high current. All right? And that works out in the power. Now in this case it was switched because our output voltage was actually less than our input voltage. Okay, here's a question for you, a quick test. We'll deal more with household circuits in the next chapter. I think that might be the end of this chapter. A couple more. These are just sort of basic questions about power and energy. Okay, and that's all for chapter 3.